This is Calculus 2 class. Today we're going to study comparison test. Previous session, we study integral test, divergent test. Now, we're going to learn new test to determine if a series convergent, divergent. Before I introduce comparison test, let's just thinking about two theories. First one is right here. Look at the denominator, 2m plus 1. It doesn't look familiar, but when you see this series, guys, can you thinking about, looks like this one is removed right here. If it's not, 1 is right there. So we thinking about series 2n. We already know this series gonna be converged. How do I know this is converged? This one is n equal 1 to infinity. So this one is 1 over 2, 1 over 2 square, 1 over 2 cube. This is geometric series. Geometric series ratio. Ratio gonna be R. What is R? R is 1.5. So R is between negative 1 and 1, which meaning is 1.5 between the negative 1 and 1. Then this series is gonna be converged. So this is converged. Let's recheck it. How about left side? Only different here and here. Look at this, 2n plus 1, 2n. Just add 1. What are you thinking about this series? 1 over 2n plus 1. Do you think this is converged? Do you think this is diverse? What do you think? I think this one is converse. Why? We're going to use comparison test. That's what we're going to do it. Here's a very important idea is we have to know some series is converse, and we're going to compare new series to the series we already know. So that's we're going to say comparison test. So next example, guys, look at this left, 1 over n squared plus 1. Looks familiar with this one, guys? Look at this. Summation n equal 1 to infinity 1 over n squared. This gonna be p series. P gonna be 2. So this one is converse. What are you thinking about this series? So what is different? Here is n squared plus 1. Here is n squared. Only different is 1. What do you feel like? This one is converse or diverse? This one is converse also. So by using the comparison test, we gonna decide if the series converse or diverse based on the series we already knew. That's what we call comparison test. Let's do the comparison test. Comparison test is two different comparison tests. First one is direct comparison. Second is limit comparison. Comparison test is looks like here a and bn. Each term of sequence have this relationship. An is less or equal to bn. So right here an is less than or equal to bn. So here is an, bn is always positive. Then you're gonna add all together. Series gonna be an, series of bn. Which one is bigger, guys? Each term of sequence is an is always less than bn. Of course, this one is gonna be bigger because that's have all the sum of each sequence, right? Then this series say first condition is right here, bn. Summation as bn is converse, which meaning is they have sum. We don't know, but they have sum. Then summation an is less or equal to b, which meaning is this is converse. Second is gonna be, now this time summation as n equal infinity an is diverse. which meaning is they going to infinity. So how about summation of Bn? This going to infinity. Of course, this is going to infinity. This series is gonna be diverse. Okay, that's why direct comparison we're gonna use from now on, but make sure which one you're gonna use it. You wanna use it one, you wanna use it two. So here is you wanna prove this one is converse, then you're gonna find the series and this relationship AN is less than over Bn. Bn series is going to be converse. If you want to prove series of Bn is diverse, then we're going to find the sequence, each term of sequence An less than Bn, then this one is diverse. So that's you have to keep in mind. Another important thing here, we're going to use, when you're using comparison test, you're going to using two series. One is P series. Second is geometric series. Because P series, we know the series can converge divergent. Geometric series also converge or diverge depending on the common ratio. So this is key idea to use direct comparison test. Let's have the example here, guys, okay? So this one we're gonna use comparison tests until we finish all the tests. You guys might have the question about which test you're going to use it first. We're going to talk about later. We want to use comparison test about this series, how to get the idea. Look at the denominator. So here's the first one, guys, A. Look at the denominator right here, n squared plus 2n plus 3. So that's the denominator. Oh, this might be, we might using P series. So idea is a P series. P value gonna be highest degree 2. Okay. Then we're gonna thinking about n squared. So we wanna compare. But you already know summation 1 over n squared is converse. This one is converse. So we might assume summation of 1n squared plus 2n plus 3 might converge, but we have proved it. Why this is converse? So let's compare two sequence term by term. Okay. So right here, n squared plus 2n plus 3n squared. Which one is bigger? N is natural number, n is start 1. Which one is bigger? Guys, of course this one is bigger. So which meaning is 1 over n squared plus 2n plus 3 less than 1 over n squared. So this series is gonna be, we find this one is, look at this one is gonna be less than n squared. This series is gonna be less than summation 1 over n squared. But like I said, this series, right side already know this is a P series and P equal to converse. See? So then we're gonna say this is converse. Okay? So we have answered this is converse. Guys, got the idea? Let's go second one. Okay, look at this one. Summation 1n minus 10. Look at the bottom only. This one is n minus 10. Oh, what happened this one? This one is related n. Okay, which one is bigger? We're going to check out later, but we know summation of 1 of n is diverse. Which meaning is summation 1 of n diverse. We have proved this series 1 of n minus 10 greater than summation 1 of n. So let's compare n minus 10 and which one is bigger? Of course, n is bigger. because you subtract 10. So which meaning is 1 of n minus 10, 1 of n, you flip it, this one is bigger. So now this series greater than summation 1 of n. So we know this is diverse because harmonic series. So conclusion is we're gonna say this one is diverse. So this one is diverse. Okay, that's you're gonna find the series which converge or diverse based on the series we already know. Okay. Here is another example. Previous example, we use P series. This example, we're gonna use geometric series right here. So when you're using comparison test, you're gonna have two options, P series or geometric series. So let's see the first one, guys. The first one is, look at the denominator, 2 plus 3n. Oh, number is right there. Number is, you can ignore because n is increased. This sequence is increasing very fast. So I want to compare this one is just 3n, right? So we already know summation of 1 over 3n geometric series ratio gonna be 1 over 3. This one is between the 1 and -1. So you're gonna say this is gonna be converse. So all you have to, you figure it out, which sequence is bigger. So here, of course, this one is bigger because you add 2 here, then flip it. Then you're going to take a summation. So comparison tests say what, guys? This geometric series is going to be converse. Our conclusion here, this one is converse. So this one is converse. Okay, guys, make sense? Let's do another one. Let's do another one right here, guys. Let's do this one. Okay, this series is going to be 3n, 7 plus 5n. So this one is compared something else. Problem is going to be this number. So we assume I want to compare this one is 3n over 5n. So this one is rewrite it 3 over 5 and right there. So this one is ratio gonna be between 3 over 5, 1 and -1. Oh, this series gonna be converged. You already know that. So what you have to compare two sequence first, but you can't compare right away. So right here, 7 plus 5n greater than 5n. Then you're gonna flip it. 1 over 7 plus 5n less than 1 over 5n. You're going to times 3n over 7 plus 5n less than 3n over 5n. So based on this one, guys, look at this one based on this. Now, we already know this series gonna be here, guys. Let's gonna be here a little out of space. Okay, so what are you gonna say? This one is converse. This one is converse. So this one is converse. So we're gonna prove it here. This one is also converse. Guys, make sense? So here is the how you get the idea about comparison test is you want to compare two tests, but one series you have to already knew. So that series is going to be P series or geometric series. Then you're going to compare each term of sequence first. Then we're going to prove this series is going to be convergence and divergent. Next one is limit comparison. So previous one, we say direct comparison. We're going to compare term by term of sequence, but sometimes it doesn't work that way. So look at the first one right here, guys. Look at this one. We already feel like this one is converse. You have idea. This might be converse. So you want to prove it. So you want to prove it 2n minus 1, 2n. Which one is bigger? Of course, this one is bigger, right? This one is bigger. Then you're going to flip it. 1 over 2n minus 1, 1 over 2n. This one is bigger. We want to prove this one is converse, but this one is greater than this. This one is converse. This one converse. Does not guarantee. One over this one is converse. This one is problem. So feel like this left series is gonna be converse, so we cannot using comparison test, direct comparison test. So in that case, we're gonna do limit comparison test. Same thing is right here, guys. Look at this one. Here is NQ minus 1, only minus 1. Here's NQ. You know that this is converse. P series. Then you're gonna guess this is also converse, but you want to prove it. So let's comparison n cube minus 1 n cube. Which one is bigger? N cube. We have the same problem. 1 over n cube minus 1, 1 over n cube. This one is bigger, left side. So we cannot say this series is going to be converse. Converse. Because of, we cannot say, guys, n equal 1 to infinity, n over n cube converge. Okay, so we cannot say that. That case, we cannot using direct comparison test. I'm gonna introduce limit comparison test. Next slide. Limit comparisons stay more intuitively you're gonna find it. So we don't have to compare term by term of each sequence. We're just looking for the limit of ratio. So you're gonna say you're gonna find the limit of ratio. I showed this one. You can, or you can using this one, limit bn over an. So it doesn't matter. You're gonna using this limit. Also, you can use it. So limit is gonna be between 0 and infinity. Then you're gonna using this one. Both series gonna be converse. Both series gonna be diverse. All you have to do, check the limit of ratio of two sequence. So that's what you have to do it, guys. So you're gonna pick this one, you're gonna using this limit, or you're gonna using this limit. Then that limit exists. Very carefully, it's 0. We're gonna try different tests. It's not, or it's not going to infinity. Then we're gonna using this limit comparison test to determine if a series is convergent or divergent. This limit comparison test also you need two series, but one series you have to know if that series converges or diverges. Otherwise, you cannot use in comparison test. Let's have the example for the limited comparison test. Before we start, you intuitively know if this series converge and diverge. So let's just start first one. Look at this series. Here is the problem is -1. So we think this one is related. A is related 1 over 2n. So I want to use limit comparison test. A_n gonna be 1 over 2n minus 1. B_n gonna be 1 over 2n. Then we want to find the limit n approach to infinity. Which one go to top? It's okay. 1 over 2n, 1 over 2n minus 1. This one is limit n approach to infinity, 2n minus 1, 2n. So how can find the limit? You're gonna separate 2n over 2n minus 1 over 2n. This one is cancel out. That's gonna be 1. This one going to 0 because geometric sequence ratio gonna be 1.5. So this limit you find 1. So this limit, this ratio gonna be 1. Then we know compared to series, so you already know this is converse because geometric series, this one is converse. Okay, that's how to find it. Let's go second one. What are you thinking about this one? Same thing. This is -1. So you want to compare this one is 1 over n cubed. But we cannot do the direct comparison test we discussed previous slides. So I want to find a_n gonna be 1 over n cubed minus 1. B_n gonna be 1 over n cubed. So we want to find the limit of ratio of two sequence 1 over n cubed, 1 over n cubed minus 1. So you're going to simplify this form, n cubed minus 1 n cubed. This one is infinity over infinity. So we're going to use L'Hopital rule. 3n squared over 3n squared, that's limit to 1, 2. So this limit between 0 and infinity, we already know this one is converse. Why, guys? P series P is 3. Also, this one is converse. So that's the limit comparison test. What do you think about this one? This one is much easier than direct comparison, but the main point is you have to know which series gonna be compared. So that's the key point. Which series you're gonna use? P series or geometric series. Let's have another example. This one is a little complicated, but we can do this one too, guys. So first you figure out which series is gonna compare this series. So he gonna be, we talked about already, this one is, guys, look at this. Look at the inside right here, this one. So this one is number. So this might be, we're gonna thinking about 1 over square root of 4n, okay? So I'm gonna put, we're gonna compare this one is n equal 1 to infinity, 1 over square root of 4n. That's what we're gonna do it. So what is a_n gonna be? 1 over square root of 4n minus 1. B_n gonna be 1 over square root of 4n. Let's find the limit. N approaches the infinity. 1 over square root of 4n. 1 over square root of 4n minus 1. Let's simplify limit. N approach to infinity. That's going to be square root of 4n minus 1. 4n square root. I can find the limit. Limit, we study it. Square root 4n minus 1 over 4n. That limit going to inside. Limit 4n minus 1 over 4n. You're going to using L'Hopital rule. 4 minus 4, that's going to be 1. Okay, let's prove it. So this limit of ratio going to be 1. Now, what are you going to say? This one is converse. No, this one is diverse. Guys, I'm sorry. Why this is diverse? Let's rewrite it. Then square root of 4 is 2, 1.5. So this is a P series. P series P is 1.5. This one is diverse. Right, make sense? Diverse, right. So what are you gonna say? Our conclusion is summation n equal 1 to infinity 4 square root of 4n minus 1 also diverse. Guys, make sense this one? That's how to solve this one, guys, okay? Let's try D, okay? Let's try the D. So this one is, oh, looks a little complicated, right? So let's first, you're gonna ignore this number, then we have to see the new series. So summation, square root n, and square. So that's gonna be converge diverse. Let's check this one first. So this one is summation, square root n. Here is gonna be n squared, then n times n, right? So this one is a summation. This one is cancel out. What do you left here? Square root n. That's gonna be 1 over square root n times n. This one is a summation 1 and 3 over 2. Why? Square root n times n, and 1.5 times n, add power together, and 3 over 2. So this P series, guys, you see, P series is 3 over 2. This series gonna be some converse. Why? This P series greater than and converse. That's we just know that. Now, what you have to do here, compare the sequence. And we have to find the ratio, right? So here is an square root n square. We find this one is 1 n square root n. That you find right here. Bn gonna be looks like square root n square plus 1. Guys, make sense? So let's find the limit, then figure it out. 1 of n square root n square plus 1. Oh no, I'm sorry, this is not right. That's the an. This is an, guys. This is an. This time here is bn. Square root n square plus 1. It doesn't matter which one on the top. Okay, guys, n. So this one is limit n approach to infinity. Simplify. This one is n square root n times square root n square plus 1. So you have n square plus 1, n times n square plus 1, n square. I want to using L'Hopital rule, 2n over 2n. That's going to be 1. So we know the limit of ratio of a sequence is 1. So what do you know now, guys? This one already you prove converse. Now, our conclusion is here. This series we see converse. So here's my conclusion for comparison test. You have to find the series which is converse or diverse first. Then we have to use limit comparison test or direct comparison test.